Welcome to the third part of this never-ending chapter. So right now we're going to switch gears a little bit and we're going to talk about enthalpy again. But in this case, I'm going to show you two different ways in which we can calculate enthalpy. One of the ways is going to be an indirect method, which we call Hess's law. And then we're also going to look at how we can calculate enthalpy using theoretical values. So let's go ahead, buckle up, get your calculators out, and let's just math. Enthalpy and Hess's law. Yes, I know that's not how you say it, but in my brain, all of these S's just come together to say Hess's. So my delta H, my enthalpy, is going to be a state function, which once again, it just means that it depends only on my initial and final enthalpy, not on how I got there. It doesn't matter which pathway I take. Does not matter. So what Hess's law says is that if a chemical equation can be expressed as the sum of a series of reaction steps, then the enthalpy of reaction for the overall equation is going to be the sum of the enthalpy changes for the individual steps. So we are going to start with something basic, and don't worry about this. I will break it down a little bit easier. So I have my reactants. I am trying my hardest to make ammonia. I need 3 moles of hydrogen, 1 mole of nitrogen. And I am trying to work my way towards making that ammonia. I personally hate this graphic because it means nothing to me. What I need to know is, okay, Evie, you have to make ammonia. You have N2. You need 3 moles of H2 in order, and these are gases because the state of matter matters, to make 2 moles of ammonia. That is what I need. So this equation here, the one on the top, is the one that I need to match. So I need my reactants to be on the reactant side. I need my products to be on the product side. And if they are not, I have to work with my equation. So if things are on the left and they need to be on the right, I have to flip my equation. If I have 1 but I need 7, I need to multiply by that factor. So I can do whatever I want to my equation in order to make it match the one I need to match. So you guys are never responsible for coming up with the steps, mostly because other people have done those steps before, so there's no reason for y'all to reinvent the wheel. So here is how you look at this. You look at step 1, and step 1 has 2 hydrogens and 1 nitrogen. So you look at the equation you have to match. You have 1 nitrogen, you're like, success. You also have 3 hydrogens, you're like, oh no, I only have 2. But for right now, we take what we can get. So we go ahead and keep that one as it is. In the second step, I have N2H4, which is not a thing that I actually need. But I also have ammonia, and I have 2 equivalents of ammonia as I should. If you look at the equation on the top of the page, you should have 2 moles of ammonia. So what you're doing is you're making sure that things are where they need to be. And you keep doing this thing called reading, and you notice that you also have 1 hydrogen. You're like, oh my gosh, I can now finally breathe, because you had 2 hydrogens on the equation before. Now you have the extra hydrogen that you were missing. So when you see these 2 equations, I like canceling out things that are the same on opposite sides. So I have an N2H4 on the right, N2H4 on the left. So they can go away. I also realized that things on the same side need to be added. So I have 2 H2s plus 1 H2. That gives Evie 3 whole H2s. I still have an N2. And I have my 2 ammonia. Also, I added those 2 equations. which means I have to add these two values. So I do 95.4 plus negative 187.6. It gives Evie negative 92.2 kilojoules per mole. To me, Hess's law is like putting together a puzzle. You have all of the information you need. You have what the picture should look like. And these are the pieces you have. So you're going to manipulate your pieces so you can get the final picture. So, ta-da! The best way I know how to do Hess's law is by doing it. So I am going to walk you through these examples. So the equation that I need to match, I'm going to highlight in yellow for the first one and also in yellow for the second one. Okay, so I look at my first equation here and I realize that it has C2H4. C2H4 is on the reactant sides. C2H4 is also on the reactant side in my equation. So I let that one be as is. I don't do anything. I then look at the second equation and I notice that I have C2H6. And I'm like, that sounds familiar. So I go back up to my equation and I see that I do need to have C2H6. But I realize that C2H6 needs to be on the right-hand side of my equation. In the one I was given, where is my C2H6? On the reactants, correct. So what I need to do is flip my whole equation. So I'm going to rewrite my flipped equation on the bottom of it. 2 CO2s in gas plus 3 liquid waters. They make C2H6 in the gas phase plus 7/2 O2. Whatever I do to my equation, I must do to the value of my delta H. Because I flipped my equation, I have to flip the sign. So I also rewrite, and it's now going to be positive 1560 kilojoules per mole. In order to make myself be successful, I'm going to highlight that in black so I don't see it again. And I don't think I have to use it. So it's gone. I don't see it. Okay. I look at my last equation and I notice that I have H2. Is H2 where it needs to be? Yes or no? Yeah. Is it the right amount of H2s that I need? Yes. So I don't do anything to it. So now I can go ahead and add my 3 equations. So I start looking for things that are the same on opposite sides. So I have 2 CO2s on the right, 2 CO2s on the left. They go away. I have 2 waters plus 1 water gives Evie 3 waters on the right, 3 waters on the left. Okay, so I'm gonna do you guys a solid right here. I'm gonna change this from 3 into 6/2. Okay, I have 6/2 plus 1/2 oxygen on the left, which gives Evie 7/2 oxygen. And I have 7/2 oxygens on the right. They are going to go bye-bye. So at the end of the day, what I have left is C2H4 in the gas phase plus hydrogen gas forming C2H6 gas. So now that I managed to match my equation that's highlighted in yellow, I go ahead and I put all of those numbers in my calculator. Negative 1411 plus 1560 plus negative 285.8. After you do this, you get negative, the delta H for this reaction is going to be negative 136.8 kilojoules per mole. Okay, so that is how you approach this problem. So let's do the next one. By the way, guys, I'm going to try to give you a trick. Don't mess with oxygens first, because oxygens are going to be in multiple places in multiple equations. So if you start trying to locate where your oxygens are, it's going to make your life miserable. You don't want to do that. So don't look for oxygens. Don't go chasing oxygens. It's not going to be a pleasant experience. So I look at my first equation right here, and I am ignoring the oxygens. So please, with me, ignore those oxygens. I realize that I have two NOs. How many NOs does Evie need according to the balanced chemical equation? Yeah, two. Evie needs two NOs, more than what she has. So I need four totals. I only have two. What does Evie need to do in order to get four NOs? Yeah, I need to multiply the whole thing by 2. So I go ahead, I multiply by 2, the whole shenanigans, which gives me 2 N2s of the gas form plus 2 O2s in gas form, make 4 NO in gas. Whatever I do to my equation, I must do to my delta H. So my delta H is going to be 2 times negative 180.5. Once again, the reason why I multiply by 2 is because I need 4 NOs. And this equation only has 2 NOs. So I am going to be lacking in my nitrogen monoxides. After I do that, I am going to stretch it out so I don't have to look at it again. I look at the second equation that I was given, and I notice that it has ammonias. But I have to ask myself, does it have the right number of ammonias? No. I need 4 and I only have 2. So I need to multiply by 2. But then I have to ask myself a second question. Are my ammonias where they need to be? Also, no. So I need to not only multiply by 2, I need to flip that equation. So I do that. I rewrite again, and I have 4 NH3 in the gas fashion goes to 2 N2s gas plus 6 H2s gas. So I multiply by 2. So my delta H is going to be multiplied by 2. But I also flipped the sign. So it now needs to be positive 91.8 kilojoules. Then once again, I scratch it out to make sure I don't confuse myself. Lastly, the last one. Once again, I am not looking for oxygens. I am not chasing oxygens. Don't do that. It's going to make you miserable. You deal with oxygens at the end. I look at this equation and I realize that I have water. I need water. Everyone needs water, but particularly this equation needs water. I have 2 waters. According to my balanced chemical equation, I need 6 waters. So what do I need to do? Multiply the whole thing by 3, right? That is what I need to do. So I write it out. Times 3. And that gives me 6 H2s plus 3 O2s makes 6 whole waters. I multiply by 3, but didn't flip, so I keep my sign. So 3 times negative 483.6. And once again, I highlight it away so I don't see it. Now I start looking at things that are the same on opposite sides. So I have 2 N2s, 2 N2s, they go away. 6 H2s, 6 H2s. I write down whatever is left. So I have, and I'm going to use my highlighter to make my life easier right now. Let's do orange. I have this, 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 two, two. That is all that's left. So I have 4 ammonias that are a gas, plus 2 and 3 gives me 5O2. See, guys, I told you, don't worry about the oxygens. They're going to come out right at the end. It is fine. Don't freak out about them. And I know that some of you were doubting me. First of all, because you don't know me very well. But second of all, because you're like, but what if she's wrong? I was not going to be wrong this one time. So after I do that, and I realize that my equation at the bottom matches the equation I need to match, I am home free. So all I need to do is find these values and add them all up together. So 2 times negative 180.5 plus 2 times 91.8 plus, and I take a breather because there's a lot of plussing here, 3 times negative 483.6. I hit equals, and I got an answer that is negative 1628.2 kilojoules. Ta-da! That is how you do Hess's law. Okay, so for Hess's law, my overall enthalpy change for a reaction is going to be equal to the sum of the enthalpy changes for the individual steps in that reaction. And the reason why we use Hess's law often is because sometimes those reactions have a very high energetic cost for us to do them in a laboratory. They may be too violent. The chemicals may be too noxious to go from point A to point B. So sometimes we need to take a detour and look at those other values that get us to the end. So what we did in the slide before was we were calculating delta H of reaction from individual steps. We saw that all of the reactants needed to be on the left and that all of the products needed to be on the right. My intermediates, which means it's something that is produced then consumed, need to cancel out. If I reverse my reaction, if I flipped it, I flip the sign. If I multiplied by 2, if I multiplied by 3, I multiplied my value of delta H. Whatever I do to my equation, I must do to the delta H. You can multiply, you can divide, but you have to do that same operation to the delta H of that reaction. So here we have a very generic problem. So you are combusting carbon and carbon monoxide in order to make CO2. And these are the 2 equations that you are given. So the first thing you have to do is write your balanced chemical equation. So you have carbon plus CO makes CO2, and you're like, lady, this equation is not balanced, to which I say you are correct. Ooh, this is not good. Okay. Sorry, I misread. I need to combust from C to CO. Oof, this is way better to balance. Plus O2 makes CO. I need 2. I need 2. Now I'm better. Now I'm more balanced. Oof. So, first thing, write the overall reaction. I did. After I finished sweating, I realized it was not balanced, so I balanced it. Now comes the fun part. I have to go ahead and use the equations I was given and manipulate them in a way that at the end of my operations, this is the equation that I come up with. So these are my individual steps. All of my reactants need to be on the left. All of my products need to be on the right. So I look at my first equation and you're like, yes, it has carbon. Carbon is solid. And then you're like, no, bad day. I only have 1 carbon and I need to have 2. So you have to go ahead and multiply them by 2. On the second one, you realize that your CO is on the reactant side. You're like, oh no. All you do is you flip your equation. Okay? So you flip your equation, which means you flip your sign. You multiply your equation by 2 because you need to do that. Your intermediates will cancel out. So we multiply this equation by 2. So this value needs to be multiplied by 2 as well. So we do that. We flip this equation. My delta H needs to be flipped. After I do that, and only after I have done every single step, I go in and I add my values. And that's what I get. Ta-da. So the last, well, not last part, but one of the last things we have here is going to be enthalpy of formation. Because you have no way of measuring the absolute value of the enthalpy of a substance, do you need to measure the enthalpy change for every reaction? The answer to that is no. So what scientists did was they established an arbitrary scale with the standard enthalpy of formation as a reference standard. So my standard enthalpy of formation requires a few things of me. It requires that my elements are in their standard state, which means that if you live as a solid at 25 degrees Celsius, you're in the solid state. If you live as a molecule, which means you come in a package of 2, like hydrogen, you are in the H2 state. I also need to be at standard conditions, and my standard conditions are going to be 1 atmosphere of pressure and 25 degrees Celsius. So my standard enthalpy of formation is going to be the heat change, either gained or lost, that results when 1 mole of a compound is formed from its elements at a pressure of 1 atmosphere and at 25 degrees Celsius. So for an element in their most stable form, notice how I said element, for an element in its most stable form, that standard enthalpy of formation is going to be 0. So usually if we are not giving you a value and we are not asking you to find it, it's because that value is 0. We don't play a game in which we let you have 3 different variables. That is not what we do. If we are not giving you a value and we're not asking you to find it, it's because that value for that specific element is going to be 0. So these are going to be some of your standard enthalpies of formation. If you have a positive standard enthalpy of formation, that means that that compound is going to be less stable. The higher the number for your enthalpy of formation, the more unstable something is. So if we look at this table, the most unstable thing I can find is going to be right here. That is a pen, that's not a highlighter. Let's try again. I have O. That is going to be my most unstable thing. So I'm going to label it most unstable. And now I'm trying to find my most stable thing. So my most stable material is going to be the one that releases the most energy upon formation. So if I look through the whole table, I have a suspect, and that is going to be aluminum oxide. So aluminum oxide is going to be my most stable. Keep that in mind that that is not most stable in real life. I mean, out of the things we have on this table, it is going to be my most stable. my standard enthalpy of reaction, and you will see so many variations of this equation. It's going to be the enthalpy of a reaction that is carried out at 1 atmosphere of pressure and 25 degrees Celsius. The little knot here refers to 25 degrees Celsius and 1 atmosphere. So the way you calculate this is delta H of reaction is going to equal the sum of the moles times delta H not of formation of products minus the sum of the moles times delta H not of formation of reactants. And just like anything else, the change in enthalpy is going to be the same whether your reaction happens in one step or a series of steps. Just beating this point, enthalpy is always a state function. It doesn't matter how you get there, only your beginning and end. So one of the things that I forgot to mention is that you are going to need to know how to write the equation for standard enthalpy of formation for just one element. And I will show you how to do that. I'm going to add a slide after we finish this problem, and we will work on it. So here it says, calculate delta H naught of reaction using delta H naught of formation values. So your equation is that delta H naught of reaction is going to equal the sum of the moles delta H naught of formation of products minus the sum of the moles delta H naught of formation of reactants. So I look at what I have. I have 3 moles of CO2, 4 moles of water, 1 mole of propane. So it's moles. So I have 3 mole of CO2. 1 CO2 is worth negative 394 kilojoules per mole. To that, I am going to add my 4 mole of water times the value for 1 mole of water. That is going to give me all of my products. That is how I find my products. So I'm going to go ahead and do that calculation really quickly so I can have that number. 3 times negative 394 plus 4 times negative 286. It gives Evie negative 2326 kilojoules. Okay. From that, I need to take away the enthalpy of formation of my reactants. So I have 1 mole of propane times the value for 1 mole of propane, which is negative 104 kilojoules per mole. To that, I'm going to add the value for oxygen. You're like, woman, you did not give me oxygen. Why do I have 2 unknowns? What are you doing? To which I try to remind you again that I said, if I am not giving you a number and I am not asking you to find it, is because that value is what? 0. So, but for all intents and purposes, I'm going to write it down. Have 5 mole of O2, and it's 0 kilojoules per mole. So this gives me negative 104 kilojoules. So go ahead, math it out. Tell me what the answer is. Tell me what the answer is. I know you can't tell me because this is a recording, but I'm going to assume that you did. And the letter is B for beautiful. I am going to go ahead and give myself an extra slide to show you something. So this is the slide that I promised that I needed to add on. So one of the things that you guys are going to get asked is to write an equation that shows how to calculate standard enthalpy of formation for a compound. So what you need to do is first me get a pen going. First is make sure all elements are in their standard state. At 25 degrees Celsius in 1 atmosphere. Step 2, you need to make just 1 mole of product. You cannot be making more than 1. This means you may need fractions. So what does that mean? So if I want to make phosphorus trichloride, so example, and I'm going to give you guys a hard example first, then I'm going to do an easier one. Write the equation that corresponds to the delta H naught of formation for PCl3 gas. So here's the hint. PCl3 has to be your product. That is also going to be your only compound. Everything else needs to be elements. It's not like you can say you have PCl plus Cl2. That's not a thing. That is not a thing. That is not what you can have. You can only have phosphorus and chlorine uncombined with one another on the left. So the hardest thing is figuring out in which format these elements live. I know, Evie knows, that phosphorus lives in a group of 4. Evie knows that. There's no reason why you guys should know that, but Evie knows that. And Evie also knows that it's going to be a solid at room temperature. Evie also knows that chlorine comes in a packet of 2 and it's a gas. We're like, cool. How do I balance this? Like, what are you talking about? Like, I need to have 1 phosphorus and you, lady, are starting with 4. It's like, yeah. I want to direct your attention to this one statement I wrote here that says you may need fractions. In this case, it's not may. In this case, it's you do need fractions. So I need 1/4 of a mole of P4, and I need to have 3/2 of Cl2. This is how I would have to do this. This is a hard equation. I'm not gonna lie. I gave you the hard equation because I figured let's start with hard things. Let's do an easier one. So write the equation for, that's not how you spell any of those words, for delta H naught of formation of CO2. CO2 is a gas at room temperature, so you would have that as your product. CO2 is made out of carbon and oxygen. Oxygen is a diatomic gas, so I'm going to show that. Carbon is a solid, but carbon is weird. I have 2 allotropes of carbon. Well, technically I have 3, but for right now I have 2. I have carbon solid in graphite form and carbon solid in diamond form. Only one of them is going to be the most stable one at room temperature, and despite what the jewelry industry tells you, it is not diamond. At room temperature, my most stable form is going to be graphite. So if you look at it, I have 1 mole of carbon, solid graphite, 1 mole of O2, gas, making 1 mole of CO2. If we're going to do the same thing for water, So delta H, not formation for water. Every needs to have hydrogen, which lives as a gas and it's a diatomic. Oxygen, which is also a gas and it's diatomic. And I am going to be making H2O. That's not true. Water is a liquid at room temperature. So I need to make sure that I only have 1 mole of product, which means I need to adjust the amounts of my reactants. I cannot have a full mole of oxygen. I can only have half a mole. And no, I cannot multiply my water by 2 to get the number. I have to have 1 mole of product at all times. I cannot mess with that. So what we could also do in other cases is use enthalpy diagrams to calculate my delta H naught. So this is a different approach to using Hess's law. It is a little bit more cumbersome. It is not as intuitive, but if you are familiar with using those enthalpy diagrams, you can look at the energy differences and then manipulate them to get the value. At the end of the day, you're still going to see your CO get canceled. Your oxygens get added up and you get your product. That is the least intuitive way of doing this. So here is an example. You are trying to make acetylene from its standard elements. So your equation is 2 carbons, solid and graphite, plus hydrogen gas, making acetylene. These equations here are the ones you have to match. So you look at the first equation. You have carbon, graphite, cool. Do you have the right number of moles of carbon, solid graphite? No, you do not. So you need to multiply the whole thing by 2. So I'm going to rewrite that in red. So I have 2 carbon, graphite, plus 2 oxygens, gas, make 2 CO2s, gas. I multiplied my equation by 2. My delta H, not a reaction, is going to be negative 393.5 times 2. Then I look at the second equation. I need to have H2. I have H2. I need to have 1 mole of H2. I have 1 mole of H2, so I am good. I don't do anything else. I let it be. Let it be. Then I look at the last question, and I have 2 moles of C2H2. I need 1 mole of C2H2. I also need my C2H2 to be in the product side, and I have it in the reactants. So I need to flip this equation, and I need to divide it by 2. Or if you're a fancy person, you need to multiply by 1/2. I think it sounds fancier when I say multiply by 1/2 rather than divide by 2. So I multiply by 1/2 and I flip it. I'm going to rewrite in red. I have 2 CO2s, gas, plus 1 liquid water makes C2H2, gas, plus 5/2 O2. So I flipped my equation. So now I have 2598.8 because I flipped it. Then I also divided by 2. So I need to divide my value by 2. I check. I am going to highlight in black the things I don't need to be showing anymore. And now I start canceling things that are the same on opposite sides. So I have 2 CO2s, 2 CO2s. 1 water, 1 water. I have 2 waters plus 1/2 water. That gives me 5/2 water. 5/2 water. So at the end, what I have left is 2 graphites, 1 hydrogen, C2H2. That is what I need to do. So now I go ahead and I add all of those values. Negative 393.5 times 2 plus negative 285.8 plus positive 2598.8 divided by 2. It gives Evie a disappointing number. Delta H naught of reaction comes out to be 226.6 kilojoules per mole. Ta-da! That is how you do this problem. That is how you do this problem. Okay, so we now have another problem. So all we're doing is getting through how we go and build these equations. It says calculate the standard enthalpy of formation of gaseous diborane using the following thermochemical information. So I have boron plus 2B, 3 hydrogen gases. Boron is a solid, hydrogen is a gas, and I'm making B2H6 in the gaseous form. So I look at my first equation. I need to have 2 borons, but I only have 4. So 4 is more than 2. It is indeed more than 2. So what I need to do is divide the whole thing by 2. So now I have 2 borons, solid, plus 3 halves, O2, gas, makes B2O3, solid. I divided by 2, so my equation, my delta H, is going to be negative 2509 divided by 2. Whatever I do to my equation, I must do to the delta H. Then I look at the second equation, and I'm like, oh, that one looks ugly. Yes, it looks ugly. I need to have 3 hydrogens, but here I only have 2. So what I need to do is multiply by 3 halves. So I need to multiply the whole thing by 3 halves. So that gives me 3 hydrogens in the gas plus 3 halves oxygens, gas, makes 3 liquid waters. My delta H is going to be negative 572 times 3 divided by 2. I once again highlight in black so I don't have to see this equation again. And then the last one, I have B2H6. I have the amount of diborane I need. But is it in the right place? Yes or no? No, it is not. So I need to do what? Yeah, I need to flip my equation. So I have B2O3 of the solid fashion plus 3 waters of the liquid persuasion make B2H6 gas plus 3O2 gas. I flipped my equation, which means I need to flip the sign, and it's now going to be positive. Goes away. I now start canceling things that are the same on opposite sides. My B2O3 goes away. Huzzah! My 3 waters go away. I have 3 halves plus 3 halves. That gives Evie 6 halves, which is just 3 O2s. 3 O2s on the left, 3 O2s on the right. They go away. So now all that is left is 2 borons, 3 hydrogens, making B2H6. So go ahead, add those numbers. Tell me what you get. Negative 2509 divided by 2 plus negative 572 times 3 divided by 2 plus 2148. And we got a syntax error. Now I got 35.5. That's a highlighter. After I fix my syntax error, my delta H is going to be 35.5 kilojoules per mole. Okay, that is what I got after this calculation. Okay. So this is a weirdish question. It says the thermite reaction involves aluminum and iron oxide. My reaction is 2 aluminums plus 1 iron oxide makes aluminum oxide and liquid iron. This reaction is going to be highly exothermic. And the liquid iron that you get as a product is going to be used to weld metals. Basically, it's hot as crap. It's super hot. Like, if you look at it wrong, that is how hot it is. So, not great. The question is, calculate the heat that is released in kilojoules per grams of aluminum reacted. So, in this equation, what you're going to be doing is that delta H, not of reaction, is going to equal the sum of the moles delta H not of products minus the sum of the moles delta H not of reactants. That is going to be your approach. You have to go to the back of the book to appendix number 2. For some of the older editions, it's going to be appendix number 3. And you have to find the delta H naught for aluminum oxide. So you go there, you find it, delta H naught of formation for aluminum oxide equals negative 1669.8 kilojoules per mole. I need to find delta H naught of formation for iron 2 oxide, which is going to be negative 822.2 kilojoules per mole. I don't have to find the one for iron liquid because they were straight up nice and gave it to us. Why don't I need to find the value for the delta H naught of formation of aluminum? Why? Because you have them in their standard state. So now we go ahead and we set it up. Evie has 2 mole. Have 2 mole of Fe liquid. And I'm going to multiply by the value for Fe. It's 12.40 kilojoules per mole plus 1 mole of aluminum oxide times the value for aluminum oxide, which is negative 1669.8 kilojoules per mole. And once again, these numbers come from the back of the book. From that, I'm going to take away my reactants, which I have 2 mole of aluminum times 0, because aluminum is a solid at room temperature, plus 1 mole of Fe2O3 times the value, which is negative 822.2 kilojoules per mole. So I go ahead, I am going to solve my products first. So 2 times 12.4 plus negative 1669.8. On the top, I get, this is negative 1645 kilojoules per mole. On the bottom, it's negative 822.2. So negative 1645 kilojoules per mole minus negative 822.2. My delta H for this reaction comes out to negative 822.8 kilojoules per mole. But wait! there's more. So you are trying to find out the heat that is released per gram of aluminum reactant. So you start by saying, okay, I have 1 gram of aluminum. You always convert to moles first. 1 mole of aluminum is going to be 27 grams, but to be clear, 26.98 grams. According to this equation, for every 2 mole of aluminum, you release negative 822.8 kilojoules. So we go ahead, we multiply, divide, we do the math. 1 divided by 26.98 times negative 822.8 divided by 2. Your answer comes out to negative 15.2 kilojoules per gram of aluminum. Okay. The last thing we have that may be a little bit new is going to be the heat of the solution, or the enthalpy of solution. So the enthalpy of solution is going to be the heat that I generate or absorb whenever I dissolve a certain amount of solid in a certain amount of solvent. So my delta H of solution is going to equal the delta H of my specific solution minus the delta H of the components. So, you may notice that some salts are exo or endothermic salts. So, lithium chloride is going to be an exothermic salt. Calcium chloride is going to be an exothermic salt. These are, calcium chloride is what they use in your hand warmers. Magnesium chloride is another salt that you can use to dissolve snow on roads. So this weekend, it may be magnesium chloride. Your ammonium salts are going to be endothermic. They are going to make things cold. Sodium chloride, table salt, when you dissolve it, is going to be endothermic as well. So you're going to see a decrease in temperature with your sodium chloride when you dissolve it. Your diagram is going to help you figure out the heat of solution. So on step 1, you have to look at lattice energy. You're like, but I don't know what lattice energy is. Correct. You don't know what lattice energy is yet. We go over it in chapter 9. So my lattice energy basically is how much energy I have to add in to completely break up my salt. My lattice energy is going to be dependent on the charges of my ions as well as their sizes. But my first step is to completely break down my salt. Completely break it down. As you can expect, because I am breaking bonds, that step is going to be endothermic, which means I require energy to break those bonds. Then my second step is going to be, okay, now that I broke down my salt, I have to go in and have them mix with water. So that is going to be called my heat of hydration. Usually heats of hydrations are going to be exothermic because I am making new bonds. I am creating new interactions between particles. Every time you donate interactions, every time you make interactions, you are going to be releasing energy. At the end, you have your lattice energy plus your heat of hydration, and that is going to give you your heat of solution. That is how you tend to approach these kind of problems. That is the end of all the material, but before we go, I just want to go over a few things about thermochemistry. The first thing is that chemical reactions are always going to be accompanied by energy changes. Energy changes can be tracked using the first law of thermodynamics, which means that energy can neither be created nor destroyed. If a reaction releases energy, there must be an energy gained by the surroundings and vice versa. Delta E or delta U, depending on your textbook, and enthalpy are going to be similar in magnitude and sign, but my delta H is going to be more convenient. An exothermic reaction is going to release energy to the surroundings every single time, no exceptions, which means that my surroundings are going to get hotter. My delta H of reaction is going to be a negative value. An endothermic reaction is going to require energy from the surroundings, which means that my delta H is going to be positive. Also, because I require energy from the surroundings, I need to steal it from them. And if I am stealing their energy, I make it colder. So that is what I have to do. And this is the end of this chapter. These ideas behind thermochemistry, they are never going to leave you. They're going to carry on for, I want to say, chapter 9, when we go over a new way of calculating enthalpy. And in the next semester, if you're taking Chem 112, we will go over how to use enthalpy in association with other different thermodynamics quantities. But this is it. This is the end. Have a lovely time.